My name is yes. So my name is Dr. Mahender Aroori. So I'm working as an assistant professor in Department of Astronomy, Osmania University, Hyderabad. So today, so I'm starting with a question. So where we are living, dear students, am I audible, all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So, is there any disturbance? Please knock me. Don't shy to ask.
No disturbance, sir.
Okay, it is clear. So right, so I'm starting the session. So I'm starting the session with this question actually. So where we are living. So students, I'm requesting please in interactive mode.
On the earth we are living, sir.
On the earth we are living.
On the
Right.
earth, sir.
Okay, that is exact question. Answer. Right. So actually, this is the question where we are living actually. So actually, there are too many answers are there actually. So the first answer is, so we are living in the universe actually. The first answer is we are living in the universe actually. So the basically the universe is composed with radiation and matter, right? So you know about the radiation and matter, right? So right. So this is the universe actually. So this is the place where we are living actually. So there are many number of stars and many number of galaxies and clusters of galaxies and initial stages of star formation and everything is. This is the universe actually. This is the total universe actually. So exactly we are, the first answer is we are living in the universe actually. So the universe is universe contains the many number of stars and many number of galaxies and many number of clusters actually. So in this university, actually this image is taken by the Hubble's Space Telescope actually. So you may aware about the Hubble Space Telescope, right? So Hubble Space Telescope is the space-based telescope which is surviving the space to answer the cosmological questions actually. So this is the first answer actually. So we are living in the universe actually. So this is the Hubble Space Telescope actually. So this telescope is giving the wonderful plenty of information to answer the some unanswered questions actually. So it will give the details about our universe actually basically. So 90% of the universe we don't know actually. So that is why the people sent to the probes and probes are sent to the space actually to collect the information actually. So this is the Hubble Space Telescope actually. This is the wonderful telescope. Still it is surviving in the space actually to know the cosmological answers. So next question, next one is that this is the image taken from the James Webb Space Telescope actually. So recently the NASA sent this telescope into the space. That is the one of the Lagrangian point actually. So this is called as the James Webb Space Telescope image actually. So it also contains the n number of stars and n number of galaxies. N number of clusters of galaxies are there actually. This is the basically our galaxy. Suppose if you consider the single dot, suppose this is the white dot, this is the star. So like this is the more light is there, circular light and bar spiral lights are there. Those are called as the galaxies actually. So the first answer is we are living in the universe actually. So this is the James Webb telescope actually. Recently NASA sent to this James Webb telescope to the space to reveal the unanswered many questions actually, right? So the next answer is we are living in the Milky Way galaxy actually. So the Milky Way galaxy is the one of the galaxy in n number of galaxies in the universe actually. So this is our home galaxy. This is called as the Milky Way galaxy. So in this Milky Way galaxy, we are living actually. This is the second answer actually. The first answer is we are living in the universe. The second answer is we are living in the Milky Way galaxy actually, right? So this is the image. Actually, our Milky Way galaxy is what is the name of our Milky Way? What is the type of our Milky Way galaxy, students? What is the shape? What type of shape it takes? Milky Way galaxy.
Circular path. Oval path.
This is what actually, this is the barred spirals actually. These are the barred spiral galaxy. The Milky Way galaxy is the barred spiral galaxy actually. So this image taken by the Hubble Space Telescope actually. So now I am sharing another image. This is this image is captured by my student actually. This is the our Milky Way galaxy is the having the barred spiral shape actually. So this is the one of the barred spiral actually. This is one of the barred spiral actually. So if we capture the sky, if it is a dark sky, ఎప్పుడైనా మనం ఎక్కువ చీకటి ఉన్నప్పుడు మనం ఫోటో తీసామనుకో క్లియర్ మంచి మెగాపిక్సెల్ కెమెరాతోని ఒక స్పైరల్ కనిపిస్తుంది అనమాట. సో వీ కెనాట్ టేక్ ద పిక్చర్ ఆఫ్ ఫుల్ మిల్కీ వే గెలాక్సీ, isn't it? Why? So we are living in the Milky Way galaxy. This is our Milky Way galaxy. We cannot take the full picture of the Milky Way galaxy. Why? Students, am I audible? Students.
Yes, sir.
So why
Yes,
we are
sir.
not
Yes, sir.
capturing the entire image of the Milky Way galaxy?
Because we are living in the Milky Way galaxy, na sir.
Very good, very good. So that is the
Because-
answer actually. So right.
But due to the relative
Exactly.
afterwards.
Yes, 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 sir. So if we want to take the total picture of the Milky Way, we have to go the another galaxy, right?
Yes, sir.
So then only we have to capture the full image of the Milky Way galaxy. So this is the one of the arm of the Milky Way galaxy actually, which is taken by the one of my student. His name is Raviraja actually, Raviraja Potineni. So this is also one patch of the Milky Way galaxy. This is the one patch of the Milky Way galaxy. It contains the n number of stars actually, right? So the next answer is the our solar system actually, right? The first answer is we are living in the universe, right? The second answer is we are living in the Milky Way. The third answer is we are living in the solar system actually. So this is our solar system, right? So our solar system contains the one star, only one star, and 8 remaining planets are there. These 8 remaining planets are revolving around the sun in a particular orbits, right? So what is the type of orbit of Earth?
There are 3 types, sir.
Okay, what are those?
Circular,
Hmm.
oval path, scaled oval path.
Right, oval also known as the elliptical actually. So these are the planets. So this is the only star in the solar system. So these 8 remaining planets are revolving around the sun in a elliptical orbits actually. So not circular orbit actually. So this is the our solar system actually. Our solar system contains the one star that is called as the sun, and 8 remaining planets. So these 8 remaining planets are revolving around the sun in a particular orbits actually. So and along with these planets, there are the minor planets also there, which those are called as the asteroids and meteors and so on actually, comets. So these entire we are called as our solar system actually, right? So next answer is we are living on the Earth. You are also said actually, right? So on the Earth we are living
In India.
Yeah.
in India, right?
India.
So only India. So this is the exact answer actually. So first we are living in the universe, then we are living in our Milky Way, and then the next answer is we are living in the solar system, right? So then next answer is we are living in on the surface of the Earth actually, right? So this is the exact answer actually. This is the astronomical answer actually, right? So first answer is universe, then Milky Way galaxy, then solar system, then Earth. So if we consider the Earth, it has some atmosphere. So if we consider the Earth atmosphere, where we are living actually, we are living in the Earth atmosphere actually, right? So if we consider the Earth atmosphere, there are different types of layers are there. These are the layers of the Earth atmosphere actually. So we are living in the lowest layer, which is called as the what? troposphere.
Troposphere.
These are the distinct layers of the Earth atmosphere. So the first layer is the troposphere, then the stratosphere, then mesosphere and thermosphere and exosphere. But we are living in the troposphere actually. So we are living in the troposphere actually. So then above the troposphere there is a stratosphere, then above the stratosphere there is a mesosphere and there is a thermosphere and exosphere. So the troposphere. Yes. Any questions? Any question? Right, no question. So we are living in the troposphere actually. So if we consider the temperature profile of the our Earth atmosphere, this is the temperature profile of the Earth atmosphere actually. So if we consider our Earth atmosphere, it is basically contains it's a dry air actually. So what is the major contribution of Earth atmosphere gases? What are the major contribution of the Earth atmosphere gas? First one is what?
Nitrogen.
Very good. Next.
Oxygen.
Then
Carbon.
not carbon.
No,
Carbon dioxide.
water vapors.
Carbon
Then
Other gases.
Argon.
yes, other trace gases are etc. Actually. So the major contribution is the nitrogen and oxygen, then CO2 actually. So this is the our Earth atmospheric compositions actually. So if we consider the temperature profile of the Earth atmosphere, so this is the temperature profile actually. So if we consider the troposphere, as we move from the surface of the Earth to the upper troposphere, the temperature is decreases actually. So because if we consider the Earth atmosphere has the maximum mass is concentrated at the troposphere actually, right? So the more oxygen is there in the troposphere, that is why as we move from the higher altitudes, the temperature profile in the atmosphere is decreases actually, right? In the troposphere, from the surface to the higher altitudes, the temperature profile is decreasing actually. So likewise, so different layer, the temperature profile is different actually. So if we consider the stratosphere, if we consider the stratosphere, the temperature profile is decreasing actually. Do you understand this graph actually, right side graph? This is the graph between the temperature and altitude, height actually. So as we move from the lower heights to the higher heights in the troposphere, the temperature is decreasing. So if we consider the stratosphere, the temperature is again increasing. So if we consider the mesosphere, again it decreasing. If we consider the thermosphere, again it is it's gradually increases at higher altitudes actually. So because the temperature here is behaving, chaotic behavior is there actually. So in the troposphere, temperature decreasing, stratosphere it is increasing, mesosphere again it is increasing, thermosphere it is increasing actually. So this is basically different atmospheric layer have different chemical compositions actually. So that is why this temperature profile is behaves as a chaotic behavior actually. So different layer behaves as a different temperature profile actually. So this is the basically our Earth atmosphere. So in the Earth atmosphere, we are living in the troposphere. So these are the exact answers actually. The first answer is the universe. Second one is our galaxy, our own galaxy, which is called as the Milky Way. Then a solar system. Then Earth. On the surface of the Earth, we are living in the troposphere actually. So these are the answers actually, right? Okay. So coming to the sun actually. So the sun actually, the sun is the only star in the solar system, right? The sun is the only star in the sun. This is the real image of the sun actually. This is the real image of the sun actually. So if we see the sun with the naked eye, so that is exactly not this actually, right? So this is telescopic image of the sun actually, which is taken by the Solar Dynamic Observatory from the NASA actually. This is the current image of the sun actually. So this is the actual image actually, right? So this is the sun. The sun is the only star in the solar system, right? So the sun is the main source to all the living beings on the earth actually. So without sun, there could be no life actually. With respect to my knowledge, without sun, there could be no life on the earth actually. The sun is the main source of all the energy sources actually. If you consider any energy, behind that there is a the sun energy is there actually. So suppose I'm talking, why we are talking? The energy is receiving from the sun only, indirectly. So we are taking food actually. So the food also based on the solar radiation, it's generating actually. So that is why the sun is the main source of energy for all the living beings on the earth actually. So this is our sun actually. So there is the physical properties of the sun is there actually. So if we consider the age of the sun, that is the 4.5 into 10 to the power of 9. So the 10 to the power of 9 we are called as the billion years actually. The age of the sun is the 4.5 billion years. So if you want to consider the mass of the sun is around 2 into 10 to the power of 30 kgs. So it has huge mass actually. The mass of the sun is around 2 into 10 to the power of 30 kgs, right? So if you consider the radius of the sun, so it is around 6,96,000 kilometers. This is the radius of the sun actually. So the radius is 6 lakhs approximately. So what is the diameter of the sun, students? What is the diameter of the sun? Am I audible, all of you?
Double the radius.
How much it is? The radius is 6 lakh kilometer. So approximately. So what is the diameter? Double it. Just double it. 6 into 2, 12. 12 lakh kilometer is the diameter actually. So this is the radius of the sun actually. So if we consider the mean density, that is the 1409 kg per meter cube actually. So actually if we consider our planets, the planets are the solid objects actually. Unlike the planets, the sun is composed with the hot ball of gases actually, hot ball of plasma actually. It's not a solid object. If we consider the sun, it's not a solid object actually. Unlike our planets, the sun is a hot ball of plasma actually. It contains the sun, the entire sun contains the plasma material only. It's not a solid object actually. So the mean density of the sun is the 1409 kg per meter cube. So the average distance from the sun to the earth is that is 1.499 into 10 to the power of, that is 1 astronomical unit. That is also known as the 150 million kilometers. So the temperature, the surface temperature of the sun is around 785 Kelvin. The temperature of the core is the 15 million kelvins actually. Kelvin is called as the million actually. So that is the core. Core means that we'll discuss later actually. The core means the center of the sun actually. The core temperature is 15 million Kelvin actually. So if we consider the surface temperature of the sun is around 5000 Kelvin only. 15 million Kelvin and 5000 million Kelvin. So 15 million Kelvin temperature at the core of the sun. But if we consider the surface of the sun, that is around 5000 Kelvin only. That is the temperature gradient of core to the surface actually. The surface gravity is 274 meters per second actually, right? So what is the acceleration due to gravity on the earth? What is the acceleration due to g value of this earth, students?
That's 1.3.
That is 9.8 actually, 9.8 meters per second square actually. So 9.8 meters per second square for the gravity of the earth actually. So if we consider the sun gravity is how much? 274 meters per second square. So based on this value, you can expect how huge the sun, how celestial object the sun actually, right? So the escape velocity of the sun is 618 kilometers per second. In case of earth, what is the escape velocity of the earth actually? Basically, if there are any intermediate students, you can. Otherwise, you can learn in intermediate or degree levels actually.
11.2.
Right. So the 11.2 is the escape velocity. Escape velocity means we can escape from the gravitational influence of the Earth. That is called as the escape velocity. In case of the Earth, that is 11.2. But in case of Sun, the escape velocity of the Sun is 18 kilometers per second. So we can expect the how much big object of the Sun actually. So if we consider the chemical compositions of the Sun, the 90% of the chemical compositions is hydrogen, and the 10% is helium, and the remaining the small but 0.1% is other higher atomic number chemical compositions, carbon, nitrogen, oxygen, that is 0.1 actually. So there is a like the Earth, our planet, it also have the rotational periods based on its own axis, right? So but Sun rotates differential. There is a differential rotation is there. If we consider the equator of the Sun rotates at a different speed, and if we consider the poles, it rotates a different speed. That is why it is called as the differential rotation of the Sun actually. So if we consider the latitude region, this is the latitude region. If we consider the latitude region Sun, the rotational period is 31.8 days. If we consider the equator region, this is the equator region. Equator region takes the rotational period is 26.8 days. So that is why differential rotation is there. If we consider the equator, it takes the 25 days approximately. If we consider the poles, it takes the 31 days. So there is a difference in rotation periods on the surface of the Earth and the Sun. That is why it is called as a differential rotation actually. So we can see these are the different images of the Sun actually. Which means what? Different filters actually. By using different filters, we can capture the Sun image actually. So these are the different, based on the different filters, we can capture the Sun actually. Likewise, basically the Sun, like onions, it has many layers actually, right? That we'll discuss, right? So this is the Sun in different wavelengths actually, right? So this the Sun is in different wavelengths actually. So this is the 193 angstroms units. This is 304 angstroms. This is 171 angstroms, and this is 211 angstroms. This is 131 angstroms, and this is 335. So different wavelengths images of the Sun actually. These are right. So I have taken this today's Sun image actually. This is the today's Sun actually. This image is taken from the Solar Dynamic Observatory. SDO means Solar Dynamic Observatory. So this is the magnetogram image of the Sun actually. So on the Sun surface, there are sunspots are there. So these are black spots are there, appears in the surface of the Sun, which is called as the sunspots actually, right? Sunspots actually. So this is one of the wavelength actually. This is another image. This is a visible wavelength image. So there are dark spots are there on the Sun surface. So based if we see the Sun with the naked eye, we cannot see these dark spots actually. With the help of telescope only, we can observe these dark spots. Those are called as the sunspots actually. So these spots are rotate on the surface of the Sun. So based on that, the people are concluded that the Sun also rotating based on its own axis actually. This is in the visible wavelengths actually. This is the visible wavelengths actually. So this is another wavelength actually, right? So this is another wavelength. Different wavelengths actually. Different wavelengths, it gives the different this is X-rays actually. X-ray image of the Sun actually. The same image, right? So right. So this is the Sun in different wavelengths actually. So I'm concluding that the Sun is the source of all the living beings on the Earth actually. So if we consider any living being on the Earth, the Sun is the main source actually. The Sun is the main source for all the living beings on the Earth actually. If we consider animal, plants, birds, human beings, or any living beings, the Sun is the main source of energy actually. If we consider the plants, so the plants are living based on the photosynthesis process. It receives the energy from the energy from the Sun, and it takes the CO2 and it gives the oxygen in the atmosphere actually. So that is why the plants are surviving actually. So right, the sun is the source of all the living beings on the earth actually. So suppose the sun energy is coming from the sun, right? The solar radiation is coming from the sun is divided into different wavelengths actually. That is known as the electromagnetic spectrum actually. The electromagnetic spectrum consists of from radio waves to the gamma rays actually, right? So high energy gamma rays, X-rays, then ultraviolet light and infrared rays and radio waves. So this is called as the electromagnetic spectrum actually, right? So this is called as the electromagnetic spectrum. The sun energy in the form of the radiation, which is called as the electromagnetic spectrum actually. So it can, the solar radiation composed with many types of radiations actually. The first, the topmost rays are called as the gamma rays. After gamma rays, X-rays are there. After X-rays, there is the ultraviolet radiation is there. So in between the infrared radiation and ultraviolet radiation, there is a visible light. So that visible light we can, this is VGR actually, all the colors actually. We can visible, this is the visible range of the electromagnetic spectrum. Infrared rays are there. After visible, there is a infrared. After infrared rays, these are all radio waves actually. So what happened? This is the frequency range of the electromagnetic spectrum. This is the wavelength range of the electromagnetic spectrum actually. So right side there is a wavelength range, left side there is a frequency range actually. So this, if we consider these gamma rays and X-rays and UV rays having the high frequency actually. So gamma rays, X-rays, ultraviolet rays having the high frequency, it has the lesser wavelengths actually. So if we consider the radio waves, the frequency is minimum and wavelength is maximum actually. So the frequency and wavelengths are reciprocals to each other actually. So based on that, we are going to find the energy coming from the solar photon energy. The energy coming from the sun is calculated from the Einstein's relation. What is the Einstein's relation? Energy relation, E is equals to what? There we have E is equals to H nu. E is equals to H nu actually. So based on that, we have to calculate the energy of the gamma rays, energy of the X-rays, and energy of the UV rays and infrared rays and radio waves actually. So as we move from the radio waves to the gamma rays, the energy is increases, right? So the wavelength is decreasing actually. So higher the frequency, lesser the wavelengths actually. So this is the entire electromagnetic spectrum of the solar radiation actually. Based on this electromagnetic spectrum, there are different types of telescopes are there actually. So if we want to detect the gamma rays, we need to we need a gamma ray telescope. If we want to study the X-rays, we need to X-ray telescope. If we want to study the ultraviolet portion of the solar radiation, so we need ultraviolet telescope, UV telescope. If you want to study the visible telescope, visible light from the sun, we need a visible telescope, that is called as the optical telescope. So if you want to study the radiation from the sun in infrared portion of the sun, we need infrared telescope, and radio waves, we can we need a radio telescope. If you want to study the radiation, the radio radiation from the sun, we need a radio telescope. If you want to study the optical visible light of this sun, we need optical telescope. So based on that, based on the electromagnetic spectrum, there are these type of these different types of telescopes are there to study the light coming from the sun actually. So this is the total light coming from the sun: gamma ray light, X-ray light, UV light, visible light, infrared light, and radio lights actually. So if you want to analyze the radio light and gamma rays light, X-ray rays, the corresponding telescope we require actually. This is the total electromagnetic spectrum coming from the sun actually, right? So coming to the structure of the sun has a layers like onion actually. So we know the onion. So if you see the onion, it has many layers actually. So likewise, if we consider the structure of the sun has a layers like an onion actually. So if we consider the structure of the sun, it can be divided into two types actually. The structure of the sun can be divided into two types. One is solar interiors. The second one is the solar atmosphere actually, right? The solar interiors further subdivided into three types. One is the core, the second one is the radiative zone, and third one is the convective zone, right? So then solar atmosphere is there actually. So the based on the density and temperature and compositions of the solar atmosphere, the solar atmosphere is again categorized into four types. One is the photosphere, the second one is the chromosphere, and third one is the transition region, and the fourth one is the corona. So this is the main structure of the sun actually. The structure of the sun is divided into solar interiors and solar atmospheres actually. Again, the solar interiors is divided into three types. One is the core, that is the center of the sun. And after core, there is a radiative zone. After radiative zone, there is a convection zone. This is the solar interiors. So again, the solar atmosphere is divided into four types. One is the first layer is the photosphere. Then the next layer is the chromosphere. And after chromosphere, there is a transition region. Then there is the outermost layer, which is known as the corona. So you can see the image. So this is the structure of basically the structure of the sun actually. From here to here, this is the solar interiors actually. So the blue portion is there, that is called as the core actually. Is it visible, all of you? All of
Yes,
you?
sir.
Yes.
sir.
If you have any difficulty to see, you can knock me, right? So this is the structure of the sun actually. The blue portion, which is called as the core actually. After core, there is a reddish portion is there. That is known as the radiative zone actually. After core, there is a radiative zone. So from here to here. So after radiative zone, there is a circle is there actually. So from after above the red portion to the green portion, which is called as the convective zone actually. This is called as the convective zone actually. So these are the solar interiors actually. So core, radiative zone, and the convective zone actually. So then this is called as the solar interiors. After solar interiors, there is a solar atmosphere is there. The solar atmosphere consists of photosphere. This is the first. Above the convective zone, there is a photosphere is there. Above the photosphere, there is a chromosphere is there, and the coronal hole is there actually. So these are the corona actually. After chromosphere, there is a corona is there. So this portion where the faint portion is there now, that is called as the corona actually. That is the outermost layer of the sun actually, right? So you can see here also. So this the white portion is called as the core, and this portion is called as the radiative zone. So this is the convective zone. So above the convective zone, there is a photosphere. After photosphere, there is a reddish portion is there, that is called as the chromosphere. There is a transition region also there. After transition region, there is a corona is also there. So these granules and sunspots and prominences are the photospheric features actually that we'll discuss later. So this is the structure, internal structure and external structure of the sun actually. Right. So if you consider the solar interiors, the first the center of the sun is called as the what? The core actually. Right. So this is the core actually. The way this bluish portion is called as the core actually. So the core it occupies the core occupies the size of the core is about 0.25% of the radius of the sun. Means the 25. If you consider the total radius of the sun, out of that, the 25% of the radius of the sun is occupied by the core actually. So it extends out about the 0.25% of the radius from the center actually. From the center to 25% occupied by the core actually. The temperature is about 1.5 million Kelvin. You can expect it. How much temperature it has. The core has the huge temperature. The core has the huge temperature actually. Right. So that is the core actually. This is the center of the sun actually is a core where the nuclear fusion reaction starts actually. At the center of the sun, that is called as the core, where the nuclear fusion reaction occurs. And at this high temperature, 1.5 million Kelvin actually. At this temperature, the nuclear fission reactions are acceptable actually. Right? So the nuclear fission reactions needs high temperature. If we consider the pressure of the core is about 300 gigapascal. This is also huge pressure actually. If we consider the density, it has 1.5 into 10 to the power of kg per meter cube. So it has large density actually. So it creates the energy by process called as the proton hydrogen burning actually. So as I already given, the 90% of the chemical composition is occupied with hydrogen, and around the 9% helium composition is there, and 1% remaining elements are there actually. So in the core, the energy is generating by nuclear fission reaction actually. That is also named called as the proton reaction actually. So it means what? Hydrogen burning actually. Hydrogen burning is there. It means what? Two photons are combined to form a one helium nucleus. That process is known as what? Nuclear fission reaction actually. Fusion reaction actually. Nuclear fission reaction. So two hydrogen atoms are combined to form a one helium nucleus. So along with the one helium nucleus, a lot of energy is releasing actually. So if we consider the chemical compositions of this sun, 90% of hydrogen atoms are there actually. So right. So likewise, based on the hydrogen, due to the hydrogen burning, the nuclear fusion reactions happens. And the energy is generated in the core. The generated energy is moves towards the radiation zone actually. The generated energy in the form of gamma rays. High energy gamma rays are produced in the nuclear fusion reaction. So these gamma rays are moving away from the core and enter into the radiative zone actually. Still, these gamma rays are maintains the high temperature actually. So after the core, there is a radiative zone. This is the radiate. This is the core. The white portion is called as the core. So here the gamma rays takes the random directions actually. So it maintains the high temperature actually, right? So high temperature actually. So if we consider this is the radiative zone actually. So it also extends 0.25 25% to 70% of the radius of the sun actually. So the density is 20 grams per centimeter cube or 0.2 grams per centimeter cube. So the temperature is still the radiative zone maintains the high temperature actually. So the gamma rays produced in the core, which is moves away from the core and reaches the travels through the radiative zone actually. So what happened in the radiative zone, instead of absorption process, these gamma rays are continuously collide with the neighboring particles actually. Continually colliding with the neighboring particles actually. Likewise, the temperature is maintains high actually. So the radiation process is it's a calm zone actually, right? So when it reaches the so suppose if we consider a gamma ray or gamma ray particle, it is continuously colliding with the neighboring particles. What happens? It loses its energy actually. So it loses its energy. Loses energy, it means what? Frequency is decreasing. Frequency is decreasing. Wavelength is increasing actually. The energy of the photon decreases means what? It is why it is decreasing means it is colliding with the neighboring particle. So during the colliding process, it loses its energy actually. So the frequency of the gamma ray photon will decreases, right? Then strengthening increases the wavelength. Likewise, as we reaches the top of the radiative zone, the temperature is gradually decreasing actually. If you consider the radiative zone is the very calm zone actually. So the gamma rays are continuously colliding with the neighboring particles, and when these gamma rays are reaches the top of the radiative zone, so what happens? The temperature is decreasing, but because it loses its energy due to the colliding with the neighboring particles actually. So likewise, if we consider the top of the radiative zone, the temperature is decreases up to 2 into 10 to the power of 6 Kelvin actually. From 7 million Kelvin to it decreases to 2 million Kelvins actually, because due to collision actually. So rather than the absorption, it collision with the neighboring particle. That is why the temperature is decreasing actually. The energy is transported in the form of radiation in the radiative zone actually. The photon takes approximately 10 to 100 thousands of years to travel through the radiative zone actually. So the gamma rays released in the core, that gamma ray may take some millions of years to reach the top of the radiative zone actually. There is a that much of time it will be taken. So because what is the reason? Anyone knows? Okay, that we'll discuss later actually. So then if we consider the radiative zone, the temperature is gradually decreases up to the 2 million Kelvin. So what happened? The temperature is decreased actually if we consider the top of the radiative zone actually. So what happened in the convective region? So the absorption process is takes actually, because the temperature is very decreased actually. So due to what happened, these high temperatures still heats the bottom surface of the convective zone. This is the convective region actually. So what happened, due to the temperature, the hotter material here energy is absorbing in the convective zone actually. So this is the convective zone actually. So this is the radiative zone. So what happened, the temperature is decreased at the top of the radiative zone. The top of the radiative zone is called as the convective zone actually. So this is the convective zone actually, the bottom of the convective zone. So here the absorption process is going on actually, right? So rather than colliding with the neighboring particles, so here due to less temperature, the temperature is absorbed by the material, the plasma in the convective zone actually. So due to that, what happened, it's a plasma is nothing but it's a fluid actually. So if temperature, the plasma temperature increases, what happens? The density will decreases actually. So density will, if the density of the liquid decreases, what happens? It moves upward direction actually, right? So lesser density material moves upward direction, and higher density material moves downward direction. That process is called as the what? Convection process. So in the convective zone, the energy transported by convection process. So the convection process is more, means what? Lesser density material moves upward direction and greater density material moves downward direction. This is continuous process. Suppose we are due to high temperature, the lesser density material moves upward direction and it reaches the top of the convective zone, then it moves downward direction. This convection process is going on continuously actually. So if we consider the density of the convective zone is 0.01 grams per centimeter cube. This zone can be absorb the waves and become hotter itself actually. This hot matter circulates upwards in the process called as the convection process. So for example, when we are eating the oatmeal in a pot, so what happened? The lesser density material moves upward direction and a greater density material moves downward direction. So that process is known as the convection process actually. So in the convective zone, the energy is transported by convection process. If you consider the radiative zone, the energy is transported by radiation process actually. So these three are called as the solar interiors actually. So if you consider this is the radiative zone actually, this is the convection zone actually. So the radiation, if you consider the radiation zone, it is a calm zone actually. But if we consider the convective zone, there is some turbulence is there actually. So due to that, there is a shear-like structure is formed in between these two layers. Then there exists a tacho line actually. So in between the convective zone and the radiative zone, the thin layer is formed. That layer is called as the tachocline actually. That layer is called as the tachocline. The tachocline is the transition region of the sun. It has the 0.3 the solar masses between the radiative interior and the convective zone actually. So likewise, the transition from the differential to uniform rotation occurs in the transition layer, which is known as the tacholine. So where the magnetic field is generating actually, right? So then that is core. That is about the core, radiative zone and the convective zone. So then we are considered the solar atmosphere. so if you consider the solar atmosphere, the first layer is the photosphere actually. This is the visible surface of the sun actually. So what we are seeing with the naked eye, that is called as the photosphere. One of the layer of the sun, that is called as the photosphere actually. So if you see the we cannot see the sun directly with the naked eye. So because the solar radiation is the harmful radiation, because it contains sometimes UV radiation. Don't see the sun with the naked eye. Please use the filters, particular filters to see the sun actually. Don't see the sun with the naked eye. So if you want to see the sun during the sunset and sun rises time only, it is flexible to see the with the naked eye. Don't see the sun with naked eye except sunrises time and sunset times. All the students I'm requesting, right? So what we are seeing the sun with the naked eye, that is called as the photosphere actually. That is the one of the layer of the solar atmosphere, that is called as the photosphere actually. This is the visible surface of the sun, right? So it is around approximately the 500 kilometers thickness only. The photosphere taken the 500 kilometers thickness. The temperature of the photosphere is so. But if we consider the convective zone, the temperature is a million kelvins actually, approximately 1 to 2 million kelvins actually. So if we reaches the top of the convective zone, the temperature is decreases up to 5800 Kelvin, because the absorption of solar radiation actually, the energy generated in the radiative zone actually. So if you consider the density of the photosphere is very, very less, that is equals to 10 to the power of minus 12 kg per meter cube. As we move from the center of the sun to the photosphere, the temperature profile as well as the density profile of the solar interiors gradually decreases actually, right? So right, this is the density profile. Rho is the density, T is the temperature of the photosphere actually. The layer below which the sun becomes opaque to visible light. So if you want to see the solar, we cannot see the solar interiors actually. We cannot see the solar interiors. So we need to special equipments. We need to see the solar. We cannot see the solar interiors actually, like our Earth. So some special predicted methods are there. Based on that, we can see the solar interiors actually. That we'll discuss later. Right. So this is the photosphere. The upper part is cooler than the lower part. Actually. If we consider the photosphere, the upper part is cooler than the lower part. Actually, the photosphere. If you see the photosphere with the telescope or any filter, we can see these dark spots are there. Actually. So these dark spots are called as the sunspots. Actually. So these are the these spots are produces the magnetic activity regions. On the photosphere actually. So you can, this is the right side one is the individual spot actually. The sunspots are always pairs actually. One sunspot behaves as a negative charge and another sunspot behaves as a positive charge actually. So if you consider the sunspot, there is a dark portion is there, that is called as the umbra. There is a light dark portion is there, which is called as the penumbra actually. This is the structure of the sun actually. So this is called as the photosphere actually. So if you see the photosphere, there is a granules like structures are there. These are the lanes actually. So due to convection process, the hotter material moves upward direction, then it will become a less temperature material. That is why it looks like a dark material. So these are all called as the granules actually. These are the sunspots and these are the granules. There are super granules also there. These are called as the photospheric features actually. So right, this is the sunspot cycles actually. So the people are measuring the sunspot number of sunspots on the sun actually. So these are the sunspot cycles actually. So this is we are in solar cycle 25 actually. So it starts from the 0 to 25 actually. These are sunspot activity actually. If we take the daily sunspot number, if we plot the time versus sunspot number, we'll get the like this structure actually. So suppose if we consider this is the solar cycle 24 actually. So we are in a solar cycle 25 actually. This is 2023 year actually. We are in a maximum phase of a solar cycle actually. So this is like a one loop actually, right? So from the sunspots may sometimes zero actually. So this is the zero sunspot numbers actually. So it gradually increases. It may reaches the maximum sunspot number. When it is decreasing, that is called as the minimum sunspot number. So those are the minimum and maximum period of the solar cycles actually. So during the based on this sunspot activity, the solar radiation intensity is increases. So where there is a total sunspot numbers are more, the solar radiation also more actually. So these are the sunspots actually, right? So this is the daily sunspots activity actually. So we can also tell monthly mean sunspots, and this is the 13th month smoothened monthly total sunspot number. So this is yearly sunspot. If we collect the year-wise sunspot number and take the average, yearly we'll get 1 point. Then we'll get this one. So this is the solar cycle 24. This is the solar cycle 25. So there is a ascending phase. This is the ascending phase, means the sunspots are increases from 0 to maximum value. So it reaches the maximum value, again it decreases. That is the minimum period. This is the maximum period. So this is the sunspot cycle actually. So if we consider the sun actually, so this is the sun actually. This is the equator portion. So the sun also rotates like our Earth, but sun is not a solid object. It's a hot ball of plasma actually. So the sun also rotates about its own axis with respect to its own axis actually. So based on the sunspots, where the people are detected that the sun also rotating with respect to their own axis actually. So if we consider the rotation period of the sun at equator, it takes the 25 days. It takes the 25 days to complete one rotation. But as we move from the equator to the high latitude regions, so these are the northern portion of the sun. This is the southern portion of the sun. So from equator to poleward direction, if we consider the rotation period of the sun is, it takes the 35 days to complete one rotation actually. This is called as the differential rotation of the sun actually. So the differential rotation of the sun means what? The sun rotates at different rates from equator to the pole. That is called as the differential rotation of the sun actually. That is called as the differential rotation of the sun. So it means what? The rotation is fastest near to the equator and slower at high latitude regions. So this is called as the differential rotation of the sun actually. So the rotation of the sun is traced out based on the sunspot number actually. So after photosphere, there is a chromosphere actually. So this is the chromosphere takes the thickness of the chromosphere is around 25,000 kilometers. It is dimmer and more diffuse than the photosphere actually. So we cannot see the chromosphere directly. We cannot see the chromosphere directly actually. During the eclipses time only, we can see the chromosphere actually. It appears as a bright red crescent. So this is a bright red crescent is there actually. This is the during the solar eclipses time actually. So during this solar eclipse time only, the chromosphere is visible. It appears as a bright red crescent. The lower chromosphere is cooler than the photosphere actually. If we consider the lower chromosphere is cooler than the photosphere actually. At high chromosphere, if we consider the upper chromosphere, this portion, the temperature is increasing actually. This is the chromosphere. After chromosphere, these are the chromospheric features actually. So chromospheric features, we cannot see the chromosphere actually. So what we are seeing, which is called as the photosphere only, right? So if you want to see the chromosphere, we need special equipments based on the filters only we can see actually. So if we see the chromospheric features, these are the prominences are there. These are called as the bright features. We are called as the prominences. Bright patches on the chromosphere, which are called as the plages. The thread-like structures also there. These are called as the filaments actually, right? Like specules like structures or which are called as the specules actually. These are all the chromospheric features actually. We have, right? This is the chromospheric features. After chromosphere, there is a transition zone is there actually. So this is the thin and irregular layer. This is the thin and very thin and irregular layer. The temperature changes rapidly from 20,000 degrees Celsius to 1 million degrees Celsius actually. After chromosphere, there is a transition zone is there. Some transition processes occurs in this region. That is why the temperature is increases actually, right? So the temperature is gradually increases from 20,000 degrees Celsius to the 1 million degrees Celsius again. So if we consider the photosphere temperature is only 5000 Kelvin only. If we see the chromospheric temperature, the chromospheric temperature is around 7000. So, but if we consider the upper part of the chromosphere, that is called as the transition zone, from the transition zone, the temperature is gradually increasing. So because it has hydrogen is ion, very highly ionized, right? So the light emitted ions is carbon 4 and silicon 4. There are a lot of chemical compositions. These ions are emit the light, actually absorb the solar radiation and emit the radiation into the solar atmosphere. That is why the temperature is increases. There is a lot of ultraviolet region of the solar spectrum. The transition region is there is the emission of ultraviolet radiation is there, actually. This is called as the transition zone, actually. After transition zone, the peculiar type of which is known as the outermost layer of the atmosphere, actually, this is called as the solar corona. So this solar corona is more dimmer and more diffuse than the chromosphere and photosphere. We cannot see the corona. We cannot see the corona directly. Actually, we can see the corona during the eclipses time, or artificial eclipses also there, which is known as the coronagraph. So if we consider the corona temperature is gradually increases from the 1 million degrees Celsius to 2 million degrees Celsius. Actually, it extends millions of kilometers outward and merge with the interplanetary medium. IPM is called as the interplanetary medium. The medium between the sun and any planet, which is called as the interplanetary medium, actually. Right? So the corona extends millions of kilometers. Sometimes this corona is merged with our Earth atmosphere, actually. This corona is sometimes merged with the Earth atmosphere. It can be absorbed in a soft X-ray, hard X-ray, extremely ultraviolet, gamma rays, and infrareds, and radio frequencies. And the major source of the corona is the solar wind, actually. Right? So this is outermost layer of the corona, actually. Right? So these are the coronal features. Helmet streamers are there. Helmets like structures are there. These are called as the helmet streamers. Polar plumes are there. These are called as the plumes, actually. Coronal loops are there. Loop-like structures are there. These are coronal loops, actually. So at the poles, there is a coronal holes are there. These are called as the coronal features, actually. So after the solar wind, actually, we need to know about the solar wind, actually. Right? The solar wind is a stream of charged particles released from the upper atmosphere, that is called as the corona, actually. So the corona is releasing the highly charged particles, which are called as the solar wind is nothing but the highly charged particles, actually. So these charged particles are moves away from the sun atmosphere, outermost layer of the atmosphere, that is called as the corona. This is called as the solar wind, actually. The solar wind is nothing but the stream of charged particles, which is accelerated away from the sun surface and interact with the planetary atmospheres, actually. This plasma mostly consists of electrons, protons, and alpha particles with kinetic energy between 0.5 and 10 kilo electron volts, actually. The source of the solar wind is the sun's corona, where the temperature is high, that the sun's gravitational force is insufficient to trap these particles, actually. Right? So these the charged particles are accelerated away from the sun, actually. So you can see that this is the sun, actually. This is the solar wind, acceleration of solar wind, actually. The solar wind speed at maximum at the polar regions, then the equator regions, actually. Right? The solar wind speed is greater at poles and lesser at equator regions, actually. This is the solar wind. Solar wind is nothing but the stream of charged particles. So then we can see the temperature profile of the solar atmosphere. This is the temperature profile of the solar atmosphere. So see, so this is the corona, this is the chromosphere, this is the photosphere, actually. So as we move from the photosphere to the corona, the temperature, if we consider the photosphere, the temperature profile is decreased, actually. Right? So this is the temperature profile, decrease. If we reaches the chromosphere, the temperature is more or less here constant. Then from the transition region to it gradually increases to the million degree Kelvin, actually. Right? So if we consider the sun center, it maintains the million Kelvin, 15 million Kelvin. If it reaches the photosphere, the temperature is 5000 Kelvin. Again, if you reach that outermost layer of the layer of solar atmosphere, which is called as the corona, it maintains the again million kelvins actually. So there is a chaotic behavior of the temperature profile in the solar interiors and solar atmosphere actually. Right? This is the temperature profile actually. So there is a heliosphere is there actually. This is called as the heliosphere actually. So the heliosphere is nothing but the how far the solar radiation pressure is acts, that is known as the heliosphere. The solar wind reach a point where it is cool and weak that it can no longer expand against the pressure of the interstellar wind actually. So these solar wind reaches the extreme boundary of the our solar system actually. So up to that place the solar wind is reaches actually. So where the interstellar radiation pressure and this solar radiation pressure is balanced. So that point we are called as the heliopause actually. Heliosphere is the how much distance the solar radiation pressure is influenced. That is called as the heliosphere. The heliopause is nothing but the where the solar radiation pressure balanced with the interstellar radiation pressure. Interstellar radiation means the radiation coming from the other stars and other galaxies. So those pressures are balanced. That is the boundary of the heliopause actually. So this is the interstellar wind actually. So this is heliopause actually, right? So that is the heliopause, right? So the next concept is there is a different there is sorry, right. So there are some active regions are there actually. This is called as the solar flares actually, right? The solar flares is nothing but the solar flares is nothing but a flare is defined as a sudden, rapid, and intense variation in brightness actually. So if you see this video, once you can check the video. His video is playing. Is it visible, all of you?
Yes,
Sir.
Okay. So what happening actually? See again. See here. This portion is see. Suddenly, amount of energy is brightening actually, right? So this is called as the flare actually. That is called as the solar flare actually. The solar flare is defined as the sudden and rapid and intense variation in brightness of the photosphere, which is called as the solar flare actually, right? So this is called as the solar flare actually, right? So you can see the full video of this. This is our sun actually, one part of the sun actually, right? So there are different types of flares are there. So X class flare, M class flare, C class flare, B class and A class flares are there. So based on the intensity of solar flares, so there are different types of flares are there. A, B, C, M, X. X is the X class flares are the maximum intensity actually. So this is called as the flare actually. This is called as the flare actually. So these are the active regions on the flare, sun actually. These are the active regions on the photosphere of the sun actually, right? So these like eruptive phenomena are we need to study. So because the solar flares are the most energetic explosions in the solar system, these effects may travel at the our Earth atmosphere. The solar flares have a direct effect on the Earth atmosphere. The intense radiation from the solar flares travels at in 8 minutes. As a result, the Earth atmosphere, Earth upper atmosphere becomes more ionized and expands, and it can be effects on the satellites and the lower atmosphere. It can be sometimes damage the satellites, electronic components. Sometimes it can damage our Earth electric grid system also. Actually, those are called as the solar flares. These are the different types of solar flares actually based on the intensity of X-ray. A class flares intensity is 10 to the power of -7, and B class is this much, and C class is this much, and X class is this much actually. So the X class flares having the peak intensity actually. So if it is a X class flare, we can predict that the solar flare is having the high energy solar flare actually. So if it is a high energy solar flare, it may reaches the earth atmospheric level sometimes actually, right? So that is called as the solar flare. So along with that solar flares, there is a coronal mass ejections also there. These coronal mass ejections also known as the eruptive phenomena on the photosphere actually. So the coronal mass ejections is nothing but say it's a blob of a ball of plasma actually. A coronal mass ejection is a significant ejection of magnetic field and accompanying plasma mass from the sun's corona into the heliosphere. So it means what coronal mass ejections means, the amount of mass is ejected away from the sun surface and it reaches the our earth atmosphere as well as the lower atmosphere sometimes. The CMEs are often associated with the solar flares. The solar flare is sometimes associated with the CMEs, and CMEs are associated with the solar flares sometimes actually. If a CME is enters into interplanetary space, it is referred to as a interplanetary coronal mass ejection. Suppose the influence of CME is up to our Earth atmosphere, which is known as the ICMEs actually. That is known as the interplanetary coronal mass ejections. So these interplanetary coronal mass ejections, based on these solar flares and coronal mass ejections, we can predict the space weather also actually. So these ICMEs are capable of reaching and colliding with Earth's magnetosphere actually, where they can cause a geomagnetic storms, auroras, and rare case damage to electron grids actually, right? So these are the coronal mass ejections. So you can see the coronal mass ejections actually. So this is the coronal mass ejection. So you can see here some amount of mass is ejected away from the sunset. This is the coronagraph actually. This white portion is covered by artificial eclipse actually, right? So then we can see the corona actually. So this is the corona actually. So we can see the corona during the eclipses time or the artificial eclipses time actually, right? So this is the CME actually. So the large amount of mass is ejected away from the sun actually. So with the speed, this speed is may reaches 500 kilometers per second to 2000 kilometers per second actually. That much speed it hits the Earth atmosphere, right? So this is the coronal mass ejection actually, right? So suppose how the sun energies interact with the space weather. This is the sun energy, sun atmosphere actually. This is the Earth actually. So the Earth behaves as a dipole in nature. It has the magnetosphere, right? So these are the magnetic field lines actually. So suppose any eruptive phenomena occurs in the photosphere, it may reaches the magnetosphere. So the magnetosphere is protecting us from the high energy solar radiation from the sun actually. So this figure shows the how the solar radiation is interact with the our Earth atmosphere. This is the Earth actually. This is the solar atmosphere. This is the Earth atmosphere actually. So if we consider the mass of the Earth with the mass of the sun, so it's a tiny particle with respect to the sun actually. So the mass of the Earth is very, very lesser. It's negligible with respect to the sun actually. So if any eruptive phenomena occurs, then these solar radiation intensity increases, then it may strongly influence the magnetosphere. So the magnetosphere means with the Earth's magnetic field lines actually. So the disturbance of magnetosphere, which is known as the magnetostorms actually. Recently we heard from the news channels Saura Tufan. Saura Tufan means it's a geomagnetic storm. The geomagnetic storms are causes these high eruptive phenomena occurs on the sun surface actually. So this is the beautiful image which is indicated the sun in the solar atmosphere, which is interact with the space weather actually. So right, this is the image actually, right? So due to this high energy solar radiations are interact with the magnetosphere, there are different types of phenomena are occurs at the high latitude regions. So one of the beautiful spectacular phenomena which is known as the aurora actually. So when the solar radiation is incident on the magnetosphere, so what happened, these magnetic field lines are always closed lines actually. So right, So these magnetic field lines are always closed lines. So these charged particles are coming from the sun and interact with the magnetosphere. What happened? So rather than penetrating into the magnetospheric magnetic lines of forces, it may gyrate along with the magnetic lines and moves towards the high latitude regions actually. Suppose this is the one of the magnetic lines. So when these charged particle interact with the magnetic field line, so rather than penetrate into the magnetic field line, it may gyrate along with the magnetic field lines and moves towards the polar region side, polar north polar and south polar region sides actually. So these energetic particles are interact with the chemical compositions in the atmosphere. Then they may scattering the light of different colors actually based on the different compositions that are known as the auroras actually. So there are these auroras are called as the polar lights. There are southern auroras are there, and northern lights and southern lights, which are also called as the northern borealis and southern borealis actually. These are called as the auroras actually. So the auroras causes the solar radiation effect only actually. So these are the different colors, these are the auroras actually. So these different colors due to the different chemical compositions at the atmospheric levels actually. So that is why suppose the solar radiation is interact with the nitrogen, it will give some color. Suppose the solar radiation, UV radiation is absorbed by the sodium molecule, it will give the yellow. So based on the different chemical compositions present in the Earth atmosphere, we have to see the different colors of the auroras actually. So there are different phenomena are there actually, radiation belts and auroras and rainbow also. Sometimes a rainbow also formed actually when the solar radiation is interact with the atmospheric chemical compositions. It may form rainbow, different colors actually. So these are the space weather connection actually. The auroras are causes the sun-earth connection, sun-earth relations actually, right? So we can discuss some the missions to the sun actually. So this there are different missions are there actually. The Russian and American peoples are many missions sent to the sun actually, but we cannot reach the sun surface because it maintains the high temperature. So these missions are revolving around the sun, and it can observe the sun atmosphere as well as the some physics of the sun actually. So this is the one of the mission orbiting solar observatory. This is the American mission actually, which works basically it studies the solar atmosphere actually, corona actually. This mission given the data from 1960 to 1975. So after that the mission collapsed actually. So after this orbiting OSO, there is a Skylab also there. So why I introduced the Skylab is the Skylab is a very well noted sun mission actually, Skylab. The Skylab is the first United States space station launched by NASA, occupied for about 24 weeks between May 1973 and February 1974. The Skylab's orbit eventually, due to the solar radiation effect, what happened, the Skylab orbit eventually decayed and it disintegrated in the atmosphere on July 11, 1979. Scattering debris across the Indian Ocean and Western latitude. Actually, so these the Skylab mission debris are our Indian Ocean and Western Australian Ocean actually. So this is a very well aware mission of sun mission actually. So after that there is a very good observatory. It is a space-based observatory, the Solar Dynamic Observatory actually. So this is the great solar space-based observatory actually. This is known as the Solar Dynamic Observatory. So the Solar Dynamics Observatory is the NASA's mission which has been observing the sun since 2010 till it is operating actually. So it has the three major instruments. Those are called as the heliosysmic and magnetoimager. And what I shown earlier, starting slides, there are different types of images are there. So these are the three basic major instruments. One is the HMI, The second one is the extreme ultraviolet variability experiment and atmospheric imaging assembly. Actually, these are the major instruments of a solar dynamic observatory. This is giving the beautiful information actually. Based on that videos and images from the solar dynamic observatory, we are studying the sun actually, right? So these are the different types of images based on the SDO we'll getting actually. So these are the different wavelengths. White light images, 170 nanometer, which gives the temperature of the photosphere, and 160 nanometers. Different wavelengths will study the different layer corresponding to the sun actually. Suppose if you want to, if we consider the 170 nanometer, we can study the photosphere of the sun, right? So we can consider the white light, that is the visible portion, 450 nanometer. We can see the photosphere only. Suppose if you want to study this 160 nanometer, so 160 nanometer means it's a high energy actually. So the wavelength decreasing means energy is increasing. Frequency also increasing actually, right? So here from white light to this is X-ray actually, flaring region, high energy actually. So the wavelength is decreasing means frequency is increasing actually. So white light image, we can see the photosphere. So here 170 nanometer, the wavelength is decreased. We can see the photosphere, top of the photosphere like that. So 160 nanometer, we can see the upper photosphere. As we move from the photosphere to the corona, the temperature is increasing. So that is why here the wavelength is decreasing. If we consider a 33.5 nanometer wavelength, we can see the active regions like sunspots, solar flares, and coronal mass ejections like that. So if we again decrease the wavelength 13.4 nanometer, we can see the chromosphere and transition region. So again, if we decrease the wavelength 21.1 nanometer, we can see the active regions and the corona. Right, we can again decreases the wavelength 19.39 nanometer. We can see the corona and hot flare plasma. We can study the flares by using this observations wavelengths. So if we see the again another wavelength 17.1 nanometer, we can see the white corona and upper transition region. Upper transition region temperature is greater than the photosphere actually, right? So if we see the 13.1 nanometer wavelength, we can see the flaring regions. I have shown the flare now. It suddenly absorbs the brightness of the sun surface, that is called as the flare. So it emits the 10 to the power of 32 eggs of energy actually. That much of energy we can study actually. So if we again decrease the wavelength, that is 9.4 nanometer, obviously it is X-ray gamma ray studies actually. So these are the different wavelengths will give the different layer of study actually, likewise, right? So also there is a one recently the NASA sent one probe that is known as the Parker solar probe. It is the eminent scientist in Parker is the eminent scientist in the solar physics actually. The Parker solar probe is a NASA space probe which is launched in the 2018 with the mission of making observations of the outer corona of the sun. So actually we can we don't know about the fully about the corona actually. So that is why we are sending the probes to the corona actually. We need to study the corona. So 90% of the 90% we don't know about the corona actually. So still there are many things we are not yet understood. So that is why we are sending probes to the solar atmosphere towards the sun or interplanetary distances actually. The Parker solar probe is the first space to fly into the low solar corona. It will assess the structure and the dynamics of the sun corona plasma and magnetic field, the energy flow that heats the solar corona and impels the solar wind, and the mechanism that accelerated energetic particles actually. So it can study the solar corona and it can study the solar wind, and it can study the what are the mechanism based on that that these energetic particles are accelerating from the sun surface to the interplanetary distance. Likewise, studies are studying the based on the Parker solar probe actually. So the last one is I'm going to discuss is that is Aditya L1 satellite actually. So this is upcoming our indigenous, fully indigenous satellite, Aditya L1, right? This is the first Indian space mission to the observation of the sun actually. This is the first mission the India is sent to the towards the sun actually. So there are 7 payloads are there on board of Aditya L1 mission. So this Aditya L1 is a multi-wavelength mission and monitors the sun in white light and infrared, ultraviolet, soft X-ray, and hard X-ray wavelengths actually. So based on all the electromagnetic spectrum wavelengths, we can study the sun by using the Aditya L1 mission actually. This Aditya L1 is India's first dedicated scientific mission to study the sun, and will be placed in a hollow orbit around the first Lagrangian point, L1 of the Sun-Earth system, so which is 1.5 million kilometers away from the Earth actually. This L1 point is, we are going to place this Aditya L1 mission into first Lagrangian point. That point is 1.5 million kilometers away from the Sun, Earth actually. Right, that is called as the halo orbit actually. First Lagrangian point we are called as the halo orbit. So this has the advantage of the based on that we can continuously watch. This is the space-based satellite actually. So there are ground-based observations are there, as well as the space-based observations are there. The space-based observations are more advantageous than the ground-based observations, because if it is a ground-based observations, there are many disadvantages are there actually. Suppose if there are a cloudy day, we cannot observe the sun actually. So if it is a space-based, so we can watch the sun continuously 24 days actually. Right, so that is the more advantage of the space-based telescopes. That is why we are sending these Aditya satellite into the space actually. Right, so the Aditya L1 satellite has the 7 major scientific payloads are there. So out of 7 scientific payloads, there is a major scientific payload which is called as the visible emission line coronagraph. So the coronagraph is nothing but the artificial eclipse, solar eclipse actually. So then only we can study the solar corona. So otherwise we cannot. So that is why we have to create the artificial eclipse, that is known as the coronagraph. That coronagraph creates an artificial total solar eclipse in space by blocking the sunlight by an occulter actually. Then we can continuously watch the solar corona actually. So this telescope will have capabilities of spectral image of the corona, invisible, radio, infrared wavelengths, and the objectives are the study the diagnostic parameters of the solar corona and dynamics and origin of the coronal mass ejections. Additional objectives are to determine why the solar atmosphere is so hot and how the changes in the sun can affect the space weather and earth climates actually. So this the VELC is the principal investigator institute is the Indian Institute of Astrophysics. The Indian Institute of Astrophysics is leads this payload actually. Next payload name is the Solar Ultraviolet Imaging Telescope, that is called as the SOOT. The SOOT will observe the sun between the 200 to 400 nanometer wavelength range, and it will provide the full disk image of the different layers of the solar atmosphere by making use of 11 filters are there actually. The sun has never been observed from the space in this wavelength range. The spacecraft being its first Lagrangian point, the SOOT shall be observing the sun continuously without interruption actually. So the principal investigators of the institute is Inter-University Center of Astronomy and Astrophysics, and co-principal investigated institutes are Indian Institute of Astrophysics and CESI, that is Center for Excellence in Space Science in India, that is Kolkata actually. The third one is the Aditya Solar Wind Particle Experiment, to study the variation and properties of the solar wind as well as the distribution of spectral characteristics. The principal investigator of institute is PRL, that is Physical Research Laboratory, which is located at the Gujarat actually. The fourth payload is the plasma analyzer packaging for Aditya, that is called as the PAPA, to understand the composition of the solar wind and its energy distribution. The principal investigation is the Space Physics Laboratory, VSSC. VSSC is called as the Vikram Sarabhai Space Center, which is located at the Kerala actually, Thiruvananthapuram. So the fifth onboard instrument of Aditya is the Solar Low Energy X-ray Spectrometer, to monitor the X-ray flares for the studying the enigmatic coronal heating mechanism of the solar corona. So that equipment SOLEXES actually. The principal investigator is the ISRO Satellite Center actually, ISAC. So the sixth one is the high energy L1 orbiting X-ray spectrometer actually. So to observe the dynamic events of the solar corona and providing estimate the solar energy used to accelerate the solar energetic particle during the eruptive phenomena. So Isaac, ISRO Satellite Center is the principal investigator, and the second investigator is the Udaipur Solar Observatory, actually, PRL. The last one is the magnetometer to measure the magnitude and nature of the interplanetary magnetic field. So by using magnetometer, we can calculate the magnetic field of the sun, actually. So for this magnetometer, the principal investigators are the physical PRL as well as the SPL, not PRL, SPL and VSSC and ISAC, actually, ISRO Satellite Application Center, actually. So this is all about the Aditya satellite, actually. I'm wind up up to this, actually. So there are many things are there. We can cover entire syllabus with this 1 hour. So if it is possible, we'll discuss a particular topic, actually. So this is our indigenous satellite that is called as the Aditya L1 mission. So I'm also working on this. I'm trying to working on this Aditya L1 satellite. So our Telugu peoples also there, actually, Dr. Vema Reddy and Dr. Shashikumar Raja. So I'm working with these peoples. Those are from Indian Institute of Astrophysics. I'm trying to correlate my work with this Aditya L1 satellite. Indirectly, I'm also working with based on this Aditya L1 data, actually. Right? I'm concluding. I'm wind upping up to here, actually.